Alright guys, today we're going to look at periodic trends, okay? Alright, so let's write it down someplace. Periodic trends. Now, here's the deal guys. In order to understand the periodic trends, you must understand the structure of the atom and the structure of the periodic table, okay? Now in the previous video, what we went over many of the properties of the groups that we need to know in terms of the periodic table, right? Now, I forgot to mention that in group 17, okay, there's a memory device in terms of how they exist at SDP. So just know, right, that the guys in group 17, okay, are diatomic here. I'll write it again. Diatomic, okay, at SDP, okay? The guys in group 17. And there's a couple other guys that are diatomic SDP also, namely hydrogen, oxygen, nitrogen, okay? And the guys in group 17, what is it, bromine, chlorine, and fluorine, and iodine, right? So there's a memory device that they use, a Hunkelberg or Brinkelhoff or something like that. I say Hun group 17, but either or, just know, right? The guys in group 17, by themselves, SDP, they exist as diatomic molecules. That's simply two atoms stuck together in a covalent bond, but we'll talk about covalent bonding later. Also, guys, it's a bit of trivia. The guys in group 18, the guys with full valence shells, very, very unreactive, right? Noble gases. They tend to exist as individual monoatomic atoms, right? Monatomic in nature, okay? So what does that mean? Single individual units, okay? For example, if you have neon right here, noble gas, each individual guy will be a neon, okay? They tend not to be bonded to anything else due to their very low reactivity of them having a full valence shell. Okay, so let's move to periodic trends. Now, in order to understand periodic trends, as I said before, you got to understand the structure of the atom and the structure of the periodic table. Now, before we do anything in terms of memorizing what are the trends and how do they go up, down, and so on, you have to know, folks, the A word, okay? Now, we talked about Coulombic attraction, right? Now, to make life simple, let's just call it attraction. And we have said before previously that opposites attract, right? Now, there's two factors that we need to know that are going to govern how well something attracts something else, okay? So we know opposites charges attract. So we know it's going to be positive and negative, yes? Okay. So, the Coulombic attraction is governed by two factors. Now, let's say, right, you have 5 positive charges, okay, attracting, I don't know, 3 others, 3 negatives. And you have 1 positive attracting 1 negative, all right? This situation here, the 5 positives and the 3 negatives, that represents a higher attraction, right? A higher attraction than the situation with just 1 positive and 1 negative. So what's the factor? The amount, okay, or the magnitude of the charge that you have, okay? So once again, amount of magnitude plays a very, very big factor in our topic of attraction. Another guy that's going to play a big factor is this. Let's say I have this positive right here. Can you guys see that? I'll make it bigger. Okay, can you see this red? Bam. Okay, yes, my positive. All right. And a negative right there. All right. 1 of each. Positive and negative, right? And I have a positive again here. But this time the negative's way over here someplace. All right? It's way over there. Which situation has a stronger attraction? So we have this versus this, okay? And hopefully, right, you would say that this guy right here, the attraction will be stronger than this guy right here. So what's the factor here, folks? The factor here is distance, right? So we have distance, okay? And we have amount or magnitude of charge. Two of those guys right there are going to affect how much the attraction is going to take place. Okay, so no problem. So now we know already that attraction is affected by distance and is affected by amount or magnitude. We can now talk about the trends. So let's do that right now. So there are four main trends, guys, they ask you about. There's ionization energy. Okay. IE for short. Okay. There's electronegativity. Electronegativity. There's metallic character. Okay, and there's atomic radius. You guys can see that? Bam. So, what's ionization energy? Ionization energy, right, is simply, I'm abbreviating this definition, right? It's simply the amount of energy needed, okay, to remove a valence electron, okay? The amount of energy needed to remove a valence electron. Now in college textbooks, it's removing a valence electron of a loosely held, gas, atom, blah, blah, blah. Don't stress that too much, okay? No problem. Electronegativity, okay, is the attraction an atom has for electrons in a chemical bond. Okay? So I say in terms of electronegativity, think of tug of war. All right? Metallic character. How a substance, or how much a substance behaves like a metal. Also, how much a substance behaves like a metal, that's metallic character. And normally, what we look at in terms of metallic character is the ease with which the substance loses electrons. Okay, so the more easily that you lose electrons, the more higher metallic character. And there's other physical things too, but we go with particularly the ability to lose electrons. Okay, that's your metallic character is going to increase, but we'll talk about that later on. And atomic radius, I'm going to simplify this also. It's going to be simply the size of the atom. Okay. Now, normally in college textbooks, they have a more intricate definition, but readers level, we'll keep our definition simple, no problem, okay? All right, without losing the kinship. So, we got those four guys. So, let's look at ionization energy, and let's look at it across a period. All right, so, get stuff out of my way. Moving on. All right. So what I'm going to do, guys, I'm going to do a horizontal. Like this. Hopefully you guys can see that. Like this, right? Bam. Do that. Do a couple of guys like this. Okay. Alrighty. Let me grab my periodic table. And let's choose a period to look at. Okay, so let's look at period 4. Alrighty, so here I'm gonna put a 4. Now, guys, that 4 you see there on the outside, that's the period number, right? 4 here, and that 4 tells you how many energy levels these guys have right across. So all the guys right across have 4 principal energy levels, or 4 shells, right? No problem. So let's look at the first guy. Ready? The first guy is atomic number 19, potassium, K, right? So what we're gonna do, we're gonna put a K right here. All right, a little K right there. Okay, I'm gonna put 4 shells. Bam, 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 4 shells, okay? I'm not gonna write a configuration just yet, but I'm gonna put a 19 there. 19 protons, okay? You with me? Now all these other guys, they have what? 4 shells, 4 shells, 4 shells, all right? 4 shells, and so on. 4 shells right across. Now here, the atomic number is 19. That's 19 protons. And how many valence electrons does potassium have? It has only 1 valence electron. Now what I'm gonna do, rather than fill in all of these guys right here, we're gonna imagine, right? We're at the end, we're at something like bromine, okay? We're gonna compare potassium to bromine, okay, guys, group 17. So we're gonna imagine this is group 17, see, right here, okay? All right, so that's our group 17 guy right here. This is bromine, all right, so let me fill it in. This is our Br. Br has 35 protons, if I'm not mistaken. That's 4 shells, bam, 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 bam. But this time, right, it's going to have 7 valence electrons. 7 valence electrons. So what are we looking at? We're looking at 19 protons attracting 1 valence electron versus 35 protons attracting 7 valence electrons. So the question you're going to ask yourself, right? Who has more attraction? And what do we talk about in terms of magnitude, right? Who has a higher magnitude? Who has a higher amount of charge? Is it 19 and 1, or is it 35 and 7? Okay? Hopefully you said 35 and 7, right? Good. So on this side right here, we have a higher attraction between the protons and the electrons. So let's do this. The ionization energy, right, is the energy you need to come along and pull off a valence electron. So you're trying to pull off this 1 valence electron here, you're trying to pull off one of the 7 right here, and it's the energy you need to take it off. Now, since this guy right here has less attraction, okay, than this guy right here, bromine has a higher attraction, okay, it's gonna take you more energy, right, to take off an electron off the valence shell, one of the 7, then it's gonna take you to take off this 1 valence electron right here. How come? Higher attraction. So here's the deal, folks. In terms of ionization energy, IE for short, okay, as you go, I'm gonna put here across a period, your ionization energy increases. Now guys, you can look on table S, right? Table S is like a cheat code on your reference table, and you can look at the values, right? So it increases. But if they ask you on an exam or something like that to explain why, how would you explain it, right? Explain it in terms of attraction simply. As you go from left to right, there's more attraction between the protons in the nucleus and the valence electrons. Bam, you're done. It's harder for you to take off an electron off that side rather than this side. Remember, that side is a non-metal side, right? And non-metals have higher ionization energies than metals. We're gonna talk about metals and non-metals in another video. No problem. Okay, so we're looking at across a period, right? We just figured out ionization energy. Now let's jump to the next guy. Let's jump to electronegativity, EN. What would you guess is gonna happen? The ability to attract or pull electrons towards yourself, right? Okay, who's gonna have a strong attraction? Who has a strong attraction? It's gonna be bromine. How do you know? You got 35 protons, right? 7 valence electrons. Compared to what? 19 and 1. So bromine, right, on the right side has a higher affinity or a higher ability to pull electrons towards himself, okay? So, as you go across a period, your electronegativity also increases, okay? What's electronegativity again? The ability to attract or pull electrons towards yourself, okay? So that's two guys we just did, all right? All based on attraction. Okay, so what's the next guy? Next guy is metallic character. I'm gonna put MC for short, yes? Okay, now what do metals wanna do, folks, with their valence electrons? Do they wanna gain more electrons towards themselves, or do they wanna lose them? They wanna lose their valence electrons, right? So that's one hint. Second hint, what group is potassium in? Alkali metal, right? What is this guy right here? Group 17, halogen, right? Okay, so as we go from left to right, okay, what happens is the ability to lose electrons decreases, okay? Because the attraction over here is increasing, all right? Over these guys to the right, they want to hold on to their electrons and attract more towards themselves. The guys in group 1, they're very reactive, but they want to lose their electrons to whoever they can give it to. So, okay, as you go from left to right, okay, your metallic character, your ability to lose electrons decreases. All right, hopefully that makes sense. Okay, all right, so as you go from left to right, you're losing your ability to lose electrons, okay, because the guys on the right side, due to their higher attraction, they want to gain electrons towards themselves. Okay, let's move on. Let's look at atomic radius, AR for short, right? Now guys, all these guys have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 4 shells, all right down, right? Now potassium is here, 4 shells, bromine is there, 4 shells. Now I keep saying it over and over again, folks, look at the attraction, right? You got 19 guys attracting 1 valence electron. You got 35 attracting 7 valence electrons, right? So what's gonna happen? You got 35 things in the nucleus, 35 protons in the nucleus, pulling, attracting, right, the 7 valence electrons. So what's gonna happen? As you go left to right, you will notice, right, the size of the atom getting smaller and smaller and smaller. Why? Sort of kind of like the amount of electrons, right? The more electrons are pulling in the valence shell. So as you go from left to right, the increased number of electrons and increased number of protons have more attraction. And think relationship, right? You're more attracted to someone, you get closer, okay? For those of you who are dating or married or whatever, okay? So the space between the valence shell and the protons in the nucleus gets smaller, okay? So atomic radius, as you go from left to right, gets smaller or also decreases, okay? Because the shell is being pulled in more and more because of increased attraction. So let's recap one more time. Ionization energy, the energy you need to take off a electron from the valence shell, it increases from left to right. Why? Because of increased attraction. The ability to attract electrons towards yourself, called electronegativity, increases. Why? Because of increased attraction. The metallic character, the ability for you to, lose electrons, decreases. Why? Because of increased attraction. As you go from left to right, the guys are holding on to electrons more and more, right? Last one, atomic radius decreases. Size of the atom decreases. Why? Because as increased attraction, the valence shell gets pulled in more and more. All right, guys, we're gonna do downer group next in another video. All right, take care.